Greetings, my name is Jane Smith. I'm going to talk about an application of WAVEWATCH 3 to Hurricane Dorian. I'd like to acknowledge my co-authors, Ty Hesser, Mary Bryan from the Engineer Research and Development Center, Ali Abdulwali from NOAA NCEP, Aaron Rowland from BGS, IT&E, and Andrew Cox from Ocean Weather. Hurricane Dorian was a late summer hurricane in 2019. It passed through the Caribbean as a Category 1 storm, strengthened and intensified as it came to the Bahamas, slowed down, very slow transit over the Bahamas, and then carried on along the US East Coast, making a short landfall on Cape Hatteras, and then ending up in Canada. Here's some pictures of the damage done by Dorian in the Bahamas due to the wind, surge, and waves. Extremely devastating. We're applying WAVEWATCH 3. There's been a number of advances in WAVEWATCH 3. WAVEWATCH 3 is a phase average spectral wave model. We're applying it on an unstructured grid. We do that so we can have multi-scale coverage from 10 kilometers down in the order of a few meters. We use an implicit solver to get that high resolution in the nearshore and use domain decomposition to make it efficient. WAVEWATCH 3 solves the wave action equation. We're using a fully implicit integration of the advection part of the wave action equation, applying a new convergent limiter that's a mix between the Koman limiter and the Hirschbach and Janssen limiter. There's no numerical limiters on the wave breaking source term, and applying some new solvers and working to improve the efficiency in the parallel implementation. We also have a new wave vegetation source term, but it's not being applied in this simulation. Hurricane Dorian is interesting not only because it was a very intense storm, but as it tracked through the US, it came near a number of our NDBC buoys. We also have some data from satellite coverage, from satellite altimeters. So we have a pretty rich data set for doing model validation. This next slide shows the simulation of our 14-day period for WAVEWATCH 3 with the grid on the left side and the ocean weather winds on the right side. We're applying WAVEWATCH 3 at 180-second time step using the Batches and Janssen braking, LTA triads, and the ST4 source terms. Here you can see that the hurricane is starting to approach the Bahamas. It's intensifying as it tracks towards the Bahamas. It slows down as it gets over the Bahamas, spends almost 2 days, and then accelerates along the US East Coast. The color contours on the left side are wave height, and on the right are wind speed. You can see it's coming up along the North Carolina coast. It's going to pass over Cape Hatteras, and then it speeds up and also balloons up in size. As I mentioned, we have a rich set of National Data Buoy Center buoys to compare the winds and waves to. We'll march up the coast and I'll show you comparisons to both the winds and the waves. Each of these blue dots is one of the buoy locations. So the first area to look is down near Puerto Rico and up through southern Florida. There'll be a series of plots. The left panel is the wind speed and the wave height. Wind speed on the left, wave height on the right side. The blue is the modeled winds, the red is the observed, the pink is the modeled wave heights, the black is the observed. We start from the south and move towards the north. The center panel shows peak wave period, and the right panel shows both the wind and the wave directions. So in the Caribbean, the waves and winds are not so intense. There's no gauges right near the Bahamas, but as the storm passed over the Bahamas, we see the impact in southern and central Florida, looking at wind speeds of about 25 meters per second and wave heights on the order of 3 or 4 meters. And you can see good agreement. So then we move up the coast, looking at the rest of Florida and into Georgia, South Carolina. Again, we're looking at Cape Canaveral at the bottom, all the way up to coastal North Carolina at the top. These two top gauges, the storm passed right over it, so you can actually see as the winds go down as the passage of the eye. We're seeing very strong wind speeds and pretty significant wave heights too. Now we're looking at 6 to 8 meters in the wave heights. reasonable agreement in the periods and in the directions as well. Okay, we continue to move up the coast to North Carolina and Virginia. We'll talk some more later about our field research facility, which is right in this area. So now we're looking at Masonboro Inlet, North Carolina, up to Virginia Beach, still seeing some pretty intense wind speeds. Wave heights, again, are up on the order of 6 to 8 meters. We see periods look pretty reasonable and directions as well. One place where we don't do as well is right at our field research facility. We underestimate the wave heights at Duck in 26-meter depth by almost 2 meters. So we'll go back and look at that towards the end of the talk. Continue along the coast, going north, Cape Henry, up to Block Island in Rhode Island. Okay, we can see, again, good agreement in winds and waves pretty consistently. Same with periods and directions. Okay, we're going to move on to coastal Massachusetts. And again, we see the buoy out here, Georges Banks, that the hurricane passes right over. And that's this particular buoy right here. Again, some good sized wave heights up to 8 meters, strong winds, but they're starting to die out. The storm's moving faster at this point. Coast of Maine, we're going to skip over this one. It's further from the storm. It's good agreement, but not so interesting. Okay, let's go to our field research facility. We have a series of gauges that extend from 6 meters depth out here to 26 meters depth. And this is the one I showed you before. At that buoy, we're underestimating by almost 2 meters. So these simulations were done without putting in varying water levels, no tides, no storm surge. The storm surge at the FRF was up to about a meter. The green is a measured water level. The blue is predicted tide levels. So we're not including either tides or surge. And these are the winds. The blue is the wind speed up to 35 meters per second. In the wind direction, we see a very sharp turn. Before the passage of the peak of the storm, we have almost shore normal winds, and then they turn and come where they're coming almost directly out of the north. Focusing on the day the storm passes, the 6th of September, this is the 26-meter gauge. We're underestimating by close to 2 meters. 17-meter gauge, we hit pretty close, underestimating again at 11, a little less so at 8, and less so again at 6 and 5 meters. But at these gauges, they're affected by the water level. We see some shifts of periods as we go between seas and swells. And if you look at the wind and wave direction, there's a very sharp change as the storm passes. And we're a little bit lagged, a little bit later in our modeling than we were in the measurements. So to understand this better, we need to look at the wave spectra. The left side is the observations, the right is the model, time on the horizontal axis, frequency on the vertical axis, and the color contours give us the energy density, and this is on a log scale, so it emphasizes the peaks. Right here is September 6th, the peak of the storm. Now we've got the 26 meter, the deeper gauge on the top, shallower gauge at the bottom. Right as the peak is going by, we see that we've got some pretty significant swell energy, and this is coming from the southeast. And then we have a more intense wind sea locally generated that's coming from near the north. The model captures both peaks, but it's not as obvious. They're not as distinct in the model. As we move through the gauges to shallower and shallower depth, we still see that that wind sea peak is very strong and is dominating what's going on. As we get into the shallower gauges, we also see the formation of harmonics in the measurements. In the model, we see the first harmonic, but of course not higher harmonics due to the simple formulation that's being used. So the agreement looks fairly reasonable, except we don't have as intense of a wind sea peak. So we have 2 wave trains right at the peak. Out at 26-meter water depth, the wave trains are almost opposing each other. The swell coming in from the southeast and the wind sea coming almost directly out of the north. The shoreline sits at about 70 degrees at the field research facility. So very complex crossing seas. As we get into shallower depths, like the 6-meter buoy or 6-meter gauge, we see that the sea and swell are coming closer together through refraction, but we still have very strong forcing on the wind sea directly out of the north. The winds are out of the north here. So it's a very complex situation here. And it's not clear why we're underestimating the wind sea, if it's that we're not generating enough or if we're dissipating too much. Quite often when the wind sea and swell come in together at similar directions, we'll see more dissipation of the sea than the swell because the swell steepens the sea and causes additional wave breaking. Just to show you some overall statistics, these are for the buoys, the wind speed on the left, the wave height on the right. These are Taylor diagrams. What I've shown you is results from a 1.5 million node grid. You can see we're seeing very good correlation coefficient about 0.95, RMS differences on the order of 0.3. The ocean weather winds are also quite good, correlation coefficients near 0.9. Some scatter plots, the same, the winds on the left, the waves on the right. You see very good agreement as you would expect from the Taylor diagram. There's also satellite observations, and I'll show you a quick scatter plot of the satellite results on the same order of magnitude. So to summarize, Hurricane Dorian reached Category 5 status, very devastating in the Bahamas. It tracked along a lot of our NDBC buoys, so it gave us an opportunity to do some comparisons between WAVEWATCH 3 and the measurements. At this point, we've run the waves only, not coupled to storm surge. That'll come next. Took about 4.5 hours to run on 720 cores for this 1.5 million node grid. Had very high quality winds, which certainly helped in the good wave results. WAVEWATCH 3 gave us wave height correlations about 0.95. And our greatest errors were in these cases where we're on the left side of the storm. We have complex crossing seas, and we seem to be under-predicting the seas in some of these cases, as well as for the shallow gauges, we were under-predicting the wave heights due to the lack of the modeled surge. Thanks for your attention. Any comments, any questions? Thank you.